In the last video, we talked about complex numbers, and I mentioned at the end something called a probability amplitude. So in this video, I'd like to go over this mysterious probability amplitude and discuss how it relates to quantum computing and quantum mechanics in general. But before we do that, I think it's necessary to talk about some classical rules of probability. So imagine you have some state A, and this state has some probability of evolving to state B through some specified path, right? And not only that, but B can evolve to its own state C, again, through some specified path, and each of these paths have a probability associated with them of occurring. Now suppose you wanted to ask the question, what's the probability of A going to B and then B going to C? So these two things happening in succession. And we'll call that probability ABC. And classical probability theory will just tell you that it's PAB times PBC. So two events, each with their own probability, happening in succession, gives you a new probability, which is just the product of the two. So now let's examine another scenario where we're not asking what's the probability of this and this happening, but the probability of this or that happening. So now we have two paths, two mutually exclusive paths, where A can evolve from itself to B, and each of these have their own probability associated with them, right? And they're independent of one another. Either of the two could occur. So now you want to ask, okay, in this case, what's the total probability of A going to B? And classical probability theory will tell you add the two. So it's P1 plus P2. And the reason I went over this is because now we're going to construct a quantum mechanical analog to these probability rules. And instead of working with probabilities directly, we work with the thing that I mentioned in the last video, which is probability amplitudes. So a probability amplitude it's simply something that corresponds to a state, a quantum mechanical state. And it's represented by a complex number. So let's think about this probability amplitude alpha. We know it's a complex number, and it relates to some quantum mechanical event happening, but it's not quite the probability of that event happening. Now there is a relationship between the two. So let's say P alpha is just the normal probability of something happening, and then alpha is our probability amplitude. And now we want to ask, how are these two things related to one another? And the way that they are related is through something called Born's rule. So P alpha is the probability of measuring some state alpha, or the state that corresponds to alpha, and the probability of that is your complex number. You take the modulus of it, and then you square it. And this is the way these two things are related. So let's examine some example. So this is a quantum state. We'll call it AQ, and AQ can go to BQ, and BQ can go to CQ. And we have probability amplitudes associated with these events. We'll call them alpha 1 and alpha 2, and these are complex numbers, right? And the reason I went over classical probability theory is because these amplitudes obey the exact same rules as classical probabilities, in that now we have two events happening in succession. So you want to ask, what's the total alpha? What's the amplitude of A going to C? Call it AC. And AC, in this case, since these are two events happening in succession, will be alpha 1 times alpha 2. But this isn't the probability. This is the probability amplitude of this whole thing happening. Now, if you wanted to ask, okay, what's the probability that I actually measure this? Then you have to take the modulus squared of this alpha AC, which is the modulus squared of alpha 1 times alpha 2. Okay, and this is just alpha 1 squared times alpha 2 squared. And this seems pretty straightforward. I mean, up until now, these amplitudes seem to be behaving exactly as a normal probability would. So why go through the effort of doing this in the first place? And the reason for that is because when we examine this other situation, where we have two possible paths of going from one state to another, we get something that's quite strange. So let's say this path has an amplitude alpha 1 associated with it, and this one has alpha 2. Now, what does classical probability theory tell us? It says add the two. So if you want to get alpha AB, you want to add alpha 1 plus alpha 2. Okay, so that seems pretty straightforward from here. But now, if we want to interpret this as what's the actual probability that I measure A going to be, let's see what happens. We take alpha AB modulus squared, which is alpha 1 plus alpha 2, the modulus squared of that, and then this is going to give us, if you just multiply it out, alpha 1 squared plus alpha 2 squared plus alpha 1, the complex conjugate of that, times alpha 2 plus alpha 1 times the complex conjugate of alpha 2. Okay, so now it starts to become clear that there's something strange going on, because here we knew we were dealing with two mutually exclusive paths, 1 and 2, and likewise we had their probabilities simply add up, but we didn't get these cross terms over here. Now, what's the deal with these cross terms? Because it seems like these two what were supposed to be independent paths are actually interfering with each other. And we get these extra terms here that we're not so sure what to do with. So let's try and rewrite this first as something that can elucidate what's going on. So actually, in the last video, I mentioned that any complex number, including these alphas, like alpha 1, can be rewritten as the magnitude of alpha 1 times some phase factor. And I'll give it an angle phi 1, right? And then alpha 1, the complex conjugate of this, will just be e to the negative I phi 1 times alpha 1. And the same goes for alpha 2. We'll call it e to the I phi 2 times alpha 2. And then the complex conjugate is e to the negative I phi 2 times the modulus of alpha 2. And remember that e to the I phi is equal to cosine phi plus I times sine phi. So now let's plug these in for our values up here and hopefully rewrite this in a way that can clear up this confusion about these two paths that seem to be interacting with one another, even though they're supposed to be mutually exclusive. So we have alpha 1 times alpha 2, e to the I phi 2 minus phi 1, and then plus alpha 1, alpha 2, e to the I phi 1 minus phi 2. And now if we use our formula here, we can factor this out and add these two phase factors and get a term that just has cosine. Phi 2 minus phi 1. So there's clearly something going on that distinguishes these quantum events from any sort of classical event we might be familiar with. And that all has to do with this term here, which we call interference. And at first it might be easy just to just to look past this and not think much of it, because you might not be entirely familiar with probabilities or what this really means, but essentially what's happening is we have what were supposed to be two independent states from one another interacting in this term. Their phase angles are, we're taking the difference of it. And this cosine term ranges from -1 to 1. So any cosine x goes from -1 to 1. But this is supposed to be some term that has to do with probabilities. So we could get something that looks like a negative probability adding up to this total term. And what could that even possibly mean? And this is a question that has stumped physicists for a very long time, and there is no clear answer to what is really going on in this interference term. It leads to certain paradoxes, like something existing in two states at once and interacting with itself across multiple states. And this is where you get the Schrodinger's cat paradox. It's from this interference term. Now, you might be wondering, what does this have to do with quantum computing? And essentially, while this term seems to be like just a peculiarity of quantum physics, it happens to also give us a way to compute things much faster. Because if we can prepare a state that has a bunch of different paths that it could evolve from, and we let it evolve, if we're clever, we can make it such that this interference term computes things for us across the entire state, across the entire superposition of states. And this might not seem clear at first, but just know that everything in quantum computing, pretty much everything, is based around this idea of making use of interference across multiple states. So in the next video, I'm going to introduce a concept called a qubit, which is a two-level quantum system. And I'm going to go over some of the mathematics behind it. And then we're going to start to think about how we can manipulate these qubits to compute some simple things for us and compare to their classical counterparts. But it all has to do with this interference thing that we have going on between these probability amplitudes. So I'll see you in the next video.